Okay. So, good evening. Welcome to the week 11 of the NPTEL course on computational complexity. And before we begin, just want to mention that the next tutorial that we have, which is week 11, week 12, that would be on 12th of October, same time. That is fine, right?
Yes.
10 a.m. to 12 p.m. And we will have one extra session. Um, okay, so I've planned it on Wednesday, 15th of October, 7 p.m. to 9 p.m. But if this is open to changes based on if there are any constraints. So that will be in the extra session. We'll just look at the summary of what all we looked into throughout the course, and if there are specific topics that you would like to discuss, then we can do that as well. So yeah, that's it. If there are any changes that you would want, then let me know by email or something. Okay. So the topics for today is communication complexity, and we
A slight disturbance because week 12 is on 12th of October. Actually, Saturday 10 a.m. to 12 p.m. was the issue.
okay,
That is why
like
I requested.
okay, for the next one also.
Yes.
Okay, so we can do it Wednesday.
Yes. That is absolutely fine.
Okay,
Wednesday
okay,
same time, no
same
issues.
time. Yeah, sure.
Yes.
So
And
we'll do
Wednesday
8.
Wednesday date is 8th
8.
of October.
Okay, same time.
Yes. Thank you so much.
Okay, sure. Okay, so yeah, so we will briefly look into this definition, although we used it previously, I guess 1 or 2 weeks ago, but let's define it again. So there's a function f from 0 1 to the n. Okay, this really need not be n and n as such. It could be asymmetric as well, but for now let's assume. Um, okay, so this x is an n bit string and y is an n bit string, and the goal is to compute xy, f of xy. Okay, but the problem is that we don't know the value of x and y altogether. So Alice knows partly the input. Alice has the first half of the input, let's say, and Bob has the other half of the input. And Alice doesn't know what is Bob's input, and Bob doesn't know what is Alice's input, but they can communicate amongst themselves. So these are the bits 0 1, and it need not be that um, once Alice sends one bit, then Bob sends another bit, and so on. It may not be like that. For Alice could send, let's say, 5 bits, and then Bob decides to speak up. But whatever it is, they have pre-decided how they are going to communicate. So this is what we call the protocol pi. So um, which is the basically the transcript um, of the communication that happens. And for a given protocol, okay, I'll just call it P. For a given protocol P, there's an associated protocol tree, which is that let's say in the protocol P that we defined, Alice sends one bit. So based on what that bit is, there are two different nodes that we could land up in. Now at this point, if Alice communicates, so this was Alice's communication, let's say. Now let's say at this point Alice decides to send another bit. So she could send a 0 or 1, based on which will end up in two different nodes. It could also happen that at this point Bob decides to speak, and based on that maybe Alice picks up next and let's say Alice picks up next. So like we said, it's not necessary that um, I mean, if Alice communicates here, then she should also communicate here. Okay. And yeah, and this keeps on going, and at the end the leaves that we get are labeled with zeros and ones. Now what does that mean? If you yeah, so this is basically the value of f of x comma y. So based on x and y, give a fixed s and a x and a fixed y, they'll keep on communicating until they land up in one leaf, and we'll read the value of at that leaf. If it says 0, then the computation of f is 0. If it says 1, then it's 1. And now we can talk about some parameters of about how good a protocol is. Okay, so in this case, uh, we assume that Alice and Bob are all powerful. That is, they can do all sorts of computation at their end and will not charge for that time or any resource for that matter. But um, yeah, but what we are interested in is we want to minimize the amount of communication that happens. So that is what we call the size of the protocol, which is how much bits of communication ended up happening in the worst case. So the deterministic communication complexity of f, which we'll denote by d of f, is defined as minimum over all protocol p, max of x comma y, the size of p of x. By this I mean this is the sorry, yeah, I'll just okay, I don't know what's a better notation though, but yeah, by this we mean the amount of communication by protocol P on input xy. By input I mean that this is Alice's input and this is Bob's input.
Uh, this point is not clear actually. So what are we? Do we have in our hand to decide the protocol? That out of the many protocols possible, we will go for the one and which minimizes this entire thing.
Yes.
Okay. So okay, all right. So then we will look for that for which values of for which protocol we are looking for a protocol which maximizes this value of x comma y.
Okay, so let's take an example. Let's say the example is our equality function. Okay, um, of x comma y. So Alice has one n bit string and Bob has one n bit string. You want to check whether they are equal. Now, what is one possible protocol? The protocol could be that Alice sends um okay, let's say that Alice sends, this is one possible protocol. Okay, Alice sends the parity of its that is summation of uh, the the bits, okay, and do a modulo 2. So if it is odd, she will send 1. If it is even, she'll send a 0. And now let's say this is the first step she does, and then Bob checks if summation yi mod 2 is equal to summation xi mod 2, and if not, then then we know that they are not equal. This is what Bob deduces. Okay, but the amount of communication we did here is just 1 bit. So here we only did 1 bit of communication so far, but the problem is that uh, if the summation yi mod 2 is equal to summation xi mod 2, that is both the summations are equal, then we don't know whether the string is actually equal to y, or is it just that they are parity wise equal. Then what does she do? She sends she sends summation xi mod 3, and then Bob will check whether if summation yi mod 3 is equal to summation xi mod 3. Okay, and if not, then Bob is going to say that they are not equal. um, then we know that x is not equal to y. Otherwise, she does the next possible thing. Okay, she sends summation xi mod 4, and this keeps on happening. This is just one possible protocol. This is not we're not saying anything about how efficient it is, but this is one possible way which is natural to think of, because if the strings x and y actually have different parity, then in one bit itself you know the answer. And let's say even if they are even, but let's say in this step it gets detected, then we have only spent uh, some 2 bits or something as of now.
Yes, yes, yes.
Okay, so but the problem is that in the worst case it may end up taking a lot of bits. Okay, so in the worst case, how much will this take? This will take n plus 1. um, yeah, in the worst case this will take n bits, because you'll do mod 2, mod 3, mod 4, all the way up to mod n. Okay.
Do we have some probabilistic analysis available for this protocol? Because I mean, it's like what is the probability of having say equal strings? Yeah, what is the probability of having different strings if their hash values are same?
Hmm.
So that kind of the thing is happening here. So like say if their mod 2 values are same, then what is the probability that their mod 3 values would also be same? And what is the probability that their mod 2, mod 3 and mod 4 values are also same, and where is the strings in fact are different?
Hmm.
So that would be, and going till the level of modern would be very, very, rare. I think that, using the common sense also, because we have one string and wherein we are getting, mod 2, mod 3, and all these values same, and despite having different strings, would be very, very rare, I guess.
Hmm. But unfortunately, there could be. So no matter how cleverly we design this protocol and what all statistics we use, uh, once you fix a protocol which uses less than n bits, there's always an adversarial argument that one can come up with, which is some worst case x and a worst case y, which will not, for which your protocol will not work correctly. So even though this looks like a very yeah, I mean, a very unnecessary sort of information that's being conveyed over and over again, but in the worst case, we will, for some examples we'll have to end up doing this. So the point is that this minimum here basically means that um, we are looking for an optimal protocol, but optimal in the sense that in the worst case, like we're looking at the worst case complexity here. For example, when we define the uh, time taken by Turing machine, we look at we don't I mean we look at what is the worst possible input, and in the worst case how much time will it end up taking, and that is how we say that the machine runs in time. Let's say it takes t time in the worst case, then we say that the machine runs in time t. So here also we are using the same notion, um, which is worst case, um, because we're looking at the worst case input here. Okay, but you could. Hmm.
Yes, but then how to get the minimum value out of? I mean, because to select the minimum value, I should have many max available to me, and then I will go for the minimum out of those max values, isn't it? So what could be the meaning of min max thing here? This is not
Hmm. So min
arc min
meaning
max. Something else is here.
we are looking for the most optimal protocol. So let's say you can come up with um, come up with some protocol that will only, let's say you can come up with a protocol that takes square root n many uh, transcriptions. So for some, so there's some exchanges that happen, and this is bounded by square root n or order square root n. So if you could show such a protocol, then you will say that d of that function is at most order n, because you could come up with one protocol like that, but there may be some better protocol.
So what if I remove this min operator from here and I only keep the max thing? And by the max thing, I would mean that we are looking for the worst case scenario. And then for the worst case scenario, I get something, and then I go for
But
because
how
then
do
the
you
worst case
define
scenario would
this?
also be unique, isn't it?
No. So worst case scenario for one protocol could be different than worst case scenario for the other protocol. Um, so let's take okay. Mm, okay. So let's look at the worst case for okay. Let me look for an example. Mm. Hmm. Okay, so let's do one thing. Okay, there's an example that's going to come up anyway. So I think it's the first, yeah, in the next question itself. So for that, we'll see different, two or three different protocols, and then let's see which, let's analyze the worst case for both the I mean all the protocols.
Sure, sure, yes.
Okay, and yeah. So I mean, it's not necessary that, I mean, there are other analysis also. So similar um, to the Turing machine world, where you have worst case notion, you have average case notion. Here also, there are such, I mean, such notions of average case complexity and so on. Will not, maybe we'll talk about it at the end, but at the moment let's stick to this definition and yeah, see some examples. Okay, so
So Alice and Bob hold subsets S and T respectively, and they wish to compute AV.
average
AVG AVG stands for
average of the um, so basically take the union of the two sets. So for example, Alice has 1 to 4 and Bob has 2 5 7. Then we'll do S union T, which is 1 2 2 4 5 6, sorry 4 5 7. So this is a multi set, generally denoted like this. If there are repetitions, we will keep them. Okay, and then we're going to compute the average of this, which will be summation, yeah, 1 plus 2 plus 2 plus divided by 6. So this is what we want to compute.
okay. And we need to prove that this decomplexity of the average is of the order of log of
Log.
n. Uh, okay. So decomplexity. So then basically, so according to the definition, we are looking for the min of the max of this p of xy. So, but then what could be the x and y here? The exchange of the elements or something else? Like say, if it is s and if it is t, then I will take so the amount of the communication by the protocol. I see. Okay. So, so then, okay. So how much? I mean, so Alice or say Alice may send her set to the Bob, and then but then log of n would mean what? So what is n here? Okay, n is the number of the elements. So like in this case, I would be requiring the d of average is equal to of the order of log of 3. Like say if there are 3 elements. So if there are n number
Okay,
of the
not really log of 3, because each element here belongs to the set 1 to n. So you're communicating that in binary. So you'll need log n bits to communicate one number.
oh, okay. So each number, okay. So okay, I understood. Fine. So in that sense, we have to prove this thing. So, but then, so I mean, what could be the cardinality of the set S which Alice may send to the Bob? Is it necessary that the subsets would be of the finite length? And since they have given that both S and T are the subsets of 1 to n, so they are of the finite length. If they are of the finite length, then I would be adding, to compute the average, I would be adding log n number of the things. How many times? Say in the worst case scenario, n number of the times. And then I take n log n divided by the number of the items divided by n, and the value comes out to be of the order of log n. This is one thing. This could be one protocol wherein we got that this is of the order of log n. However,
So,
instead of, yeah,
what is the protocol? Let me write that. So,
so
protocol
yeah,
one. Hmm.
so protocol one is that that the Alice will send her set to the Bob, entire set to the Bob,
Okay.
uh,
And then
and
Bob computes
yes, Bob computes the average
average of S union T.
S union T, and report this average back to
Huh.
the Alice if required.
So, so there are two versions of the complexity problem. One is that where Alice and Bob both need to know the answer, and the other is when you say that Alice needs to know the answer. So in this case, because Alice is sending, Bob knows the answer. But if you do the other way around, Alice will know the answer. So whichever way you want to define, that is fine. And so for now, let's stick to the definition that, let's say, only Bob needs to know. Uh,
Okay, all right,
okay,
yeah, fine.
because we already defined it this way, so let's just relax the constraint. Okay, so what is the amount of communication that happened here? Hmm. So in the worst case, size of S could be n, and um, each element is a log n bit element. So n log n is what we ended up sending in the worst case.
Yes.
So can we do better?
Oh, I see. And the complexity, because I thought the average, because if we compute the average, then we would be dividing this stuff by n.
Hmm.
Uh, the value would be on an average. Uh, so, but then we did not compute average here.
So once Bob has S and T, Bob will just compute this. There's
Okay,
no
okay.
further communication that is needed.
Yes, yes, yes. And from the communication viewpoint, okay, this solution is not the optimal one, and we are asked to come up with a protocol, and which wherein only the log n amount of the
Hmm.
communication is required.
Hmm.
And because I can immediately think of, I can immediately think of a strategy wherein this log n amount is required only if I send counters kind of a thing, because we saw this thing in the L and NL complexity class that if we can maintain only the counters, then probably the log n amount would be required.
Hmm.
So now instead of sending the actual value, what can happen, or um,
So
or say, yeah, please, yeah.
I'll just suggest one other protocol which is not optimal. I'll let you think further. I'll just suggest one more that just brings this down from n log n to n. So how does it work? So P2, what does it do? So Alice has the set S, which is a subset of 1 to n. And now I can represent this information using an n bit vector. How do we do that? So you just write a 1 in the first place if 1 is, so bit I of this vector is equal to 1 if the element I is in the set S and 0 otherwise. So if 2 is present, then we'll write a 0 here. If 3 is, sorry, we'll write a 1 here. 3 is not present, then you write a 0, and so on. So all this information can just be encoded using a 0 1 string.
Uh, yes, yes.
Okay, and
Uh,
now instead of sending the entire set S, what Alice does is she sends a shorter, compressed version of S, which still communicates the entire information. So here, Alice sends the n bit vector encode encoding set S, and then Bob computes the average, and therefore the number of um, bits that we ended up sending is just 10.
right, right.
Okay,
Yes.
so so but the I mean the login thing that we're going to get is not relevant. I mean this strategy is not relevant for that. um, all you need to think about is, can there be some part of the information that Alice can compute locally? Right now Alice is not, in both the protocols she's not computing anything, she's just sending her information as it is to Bob.
Right, right. So what can happen that Alice can compute, because now I understood that in this communication complexity, two things are important. Something
Hmm.
that is being computed locally,
Hmm.
and that local computation is being transmitted remotely, and that kind of thing. So now it can happen that Alice can compute the sum of the elements of her set locally, and
Hmm.
that would be requiring log n amount of the effort. And the Bob will compute the sum of its elements again locally, would also be requiring log n amount of the effort. And say the
Hmm.
sum, say the sum of the Alice value came out to be say 100. So Alice would just be transmitting the value log of 100 to the Bob, and rest is the responsibility of the Bob to handle.
Hmm. Okay. So yeah. Uh, okay. So this is the protocol 3, where we are saying that Alice will compute the sum of the elements in S, computes,
Yes.
and then she is going to send, I'll call this sum of Alice. So then she's going to send this sum.
So then Alice has computed the
Hmm.
sum, and she will send. I mean, this value that the sum came out to be 100,
Hmm.
and so to send this value 100, she would only be requiring log 100 number
Hmm.
of the bits.
Okay.
So
Sends the
yes,
sum to Bob.
and would be requiring say log of, in the worst case would be
In the
requiring say the log of n number of the bits to be sent.
That is correct. So the sum of any subset, um, the maximum sum that there can be is when, let's say, S is full. So S contains all the element. Then this is basically 1 plus 2 plus so on up to n. Um, okay, and this is equal to n plus n by 2. So to communicate this amount of information, you are only going to need, so this step will take log of n square, which is 2 log n amount of bits.
Right. Yes, I forgot this thing. Yeah, sum would be of the order of n square. True. Yes.
Okay, so yeah, so now Bob has this sum. Now how does Bob compute the average?
So Bob will compute the sum of its set, sum of his set, and that value would again be of the order of n square.
Bob
And then,
computes.
but then, since Bob has received this 2 log n number of the bits,
Hmm.
so then this bit somehow should get decoded at the Bob's end. So, like say I send the value log of say 100, log of say 1024 to the Bob. So Bob will receive the value 10 only. At the most 10 into 2, say
No,
20
no, no,
only.
no. So let's say the sum is 100. Okay, then we are sending the binary representation of 100,
Yes, I forgot.
which
Yes,
is
so we would be representing, yes, this number. The whatever the sum
binary
is, we would be representing to represent this count. We would be requiring log n
login.
amount of the bit. So count is ready with the Bob. So Bob will also be making the local computation at his end to compute the sum of the elements of his set, right? And say that value is 200. So then Bob will simply, and to represent this 200 number of the things, count, he may use the bits, or even you can add the value directly, the count which he receives from the Alice. In any case, I mean, we are just communicating log n number of the bits and not more than that.
Okay, so this is the okay, so this is the average.
Yes.
Okay, and Bob computes this part, and Bob gets this part from Alice, and he already knows the size of the set that he has. That's something he can see and compute. But this value is still unknown to Bob.
So which value is unknown? Okay, cardinality of the set.
Hmm.
So that won't be difficult. Why so? Because along with the sum, so in the first case, the Alice will send a message to the Bob that I would be using hash or the pound as a marker, and
Sure.
yeah,
Yeah.
and
She just
then
needs
that
to.
kind of the thing. So just along with that the sum, and then this number of the cardinality of the set can also be sent by the Alice and separated by a pound kind of a symbol.
Yeah. So yeah. So along with the sum, she also needs to send the size of the cardinality of S, and this will take the maximum cardinality is n. So this will again take at most log n bits. So altogether, this is about 3 log n bits or order log n bit protocol. And now that this value is also known to Bob, Bob can just find out the average.
Yes.
Okay, so to answer the question that we asked earlier, so let's see what are the worst case possibilities for um, hmm. Let's see what are the worst case possibility for the protocol one.
So worst case possibility for the protocol one. I mean, so where are the possibilities for the protocol one? Protocol one is fixed. I mean, the protocol one is defined, and that is how it is a protocol.
Yeah, but
So where is the worst case here?
yeah. So what do I mean by this? So let's say Alice has input as just 1 2, and Bob has some very large set 2 3 all the way up to n minus 1. Then what is the cost of this the protocol for this particular input? Alice will send uh, 1 and 2.
Yes, I understood. So the worst case would arise when Alice, the size of the Alice subset is quite big compared to the size, or in fact, the Alice sends a subset of the size n to the Bob, and in that case, the worst case situation would be n log n. Yeah, right.
Exactly.
Yes.
So that is where we defined it to be n log n. So in this case, the worst case is when uh, Alice has 1 2 all the way up to n. In this case, I guess it doesn't matter because anyway we are sending the n bit vector.
Uh, yes, this is one hot and cooling kind of the thing which we use in machine learning stuff. Yeah. So we would be requiring a vector of the size n. Yeah.
Okay, I mean we can make it sort of have this sort of variable complexity depending on the input by saying that instead of transmitting the entire n bit vector, Alice will stop at the point where she sees the last one. So after, let's say, 4, everything else is 0, then she will not send.
But then there could be a case that say the Alice subset comprises of the elements 1, 2, 3, 4, and then all of a sudden 1 lakh.
And then all of them.
All of a sudden a pretty large value, like say 1 lakh. After 4, immediately her set comprises of only 5 elements. First
Hmm.
element is 1, second is 2, third is 3,
Hmm.
and then the fourth element is 1 million, say.
Huh, which is
Uh,
n, like the worst that we can
yes,
have is n.
yes,
Then
yes,
that would be the worst case for us.
yes, right.
Okay. And yeah, so which is different from the worst case for P1, because P1 is bad when the size is very large, but P2 can go bad if the nth element is in the set.
Yes.
It could be sparse, but if nth element is there, then it's bad. And for
Yes,
this one, again, it's bad if this sum is large. If it has very large values, then in the worst case, you'll need the sum will grow, so you'll need more bits to represent that. And also, if the cardinality is large, you'll need more bits to represent that.
yes.
But
And yeah, please.
Hmm. But yeah, I mean, it makes sense to um, talk about the worst case here, so that we know that there is a guarantee that if this much communication is allowed, then the protocol will always answer correctly. So yeah, so that's why we defined it that way. This.
Yes. So we would be selecting a protocol, and in the protocol, whichever protocol gives us the min value, we will go for it. And then out of that minimum protocol, then we will consider its worst case.
Hmm.
So probably to compute this value, we will move from left to right and not from right to left.
Hmm.
Actually, then it makes sense.
That is
And the
correct.
name, yeah, and the name of the complexity is D class only or something else, or what is D of F, or
This is
don't we
the
have some name similar to NPP or L or NL kind of a thing?
hmm
Uh,
because
yeah.
yeah, because this is not defined as a class as such, but just a measure of how hard a function is.
Okay. And so how does this function F relates to the X and Y stuff? X and Y?
X
Because
and
X and
Y
Y,
are all possible inputs here. So f is um, 2n bit function to 1 bit function, then x is some part of the function, y is the other part of the function.
oh yes. I understood this. Yeah, thanks.
Okay, so hmm, okay, so let's do one more question. Mm,
So in this, the following problem, CIS. So I don't know. Okay, CIS could be some function. CIS stands for independent set or something else.
yeah,
Click
click
and independent.
independent set.
Okay, all right. For a graph, Alice is giving click, while Bob is given an independent set T. Independent set I, and Alice is given the click C.
Hmm.
Both of them need to figure out if nothing is common in between the click and the independent set, or so both of them need to figure out if the intersection of C and I is equal to pi or not, right? But then it is already a click or the independent set, so I mean, their intersection should be equals to phi only. But then show that this d complexity of this thing is less than or equals to of the order of log square n.
Hmm.
So, but then the C intersection I would always be equals to phi.
Hmm.
So, from where this question of or not arises here?
Hmm. Okay, so let's just see one example where um, this part ABCD forms a click, and hmm, something like this. There may be other edges also, but yeah. So ABCD is a click, and A, E, F, G, no, not G, A, F is an independent set because there's no, um, yeah, there's no edge between uh, these three vertices.
I see. So is it not necessary in this problem that we have a maximal click or the maximal independent set? No. Any click and any subset will
Hmm.
work. Okay. So if that is the case, then we need to solve this thing in the log square n amount of the time. And uh, so Alice has a click and the Bob has an independent set. And now they need to check that whether something is common in between their sets or not. So to know that whether something is common in their sets or not, so the situation would be like this. Say I would be requiring uh, say I would be requiring okay, so that would be the situation. Like say uh, to encode every element of the set, Alice would be requiring log n number of the bits. And but then I think that can't we use some divide and conquer kind of a thing wherein Alice sends half of her set to the Bob, and then Bob matches with the half thing. So at least if we can keep on doing this half stuff, so then we would be able to get log of something, those many number of the thing. And what that something would be required is that whatever we do half should be able to represent that again in the log n number of the bits. So that if we take the log of the log n thing, then we will get the log square n. So the protocol could be like say so Alice sends the uh, first two characters, but then this first two would be matched with all the elements of. But then what is the local computation here? What is the local computation that Alice would be doing? So the local computation could be uh, okay. So local computation could be in a graph is of the finite size. So then but then how to take the benefit of this thing that this is an instance of a click problem wherein every vertex is connected to every other vertex. So for that thing, uh, uh, how I mean which work can be done by Alice uh, so that yes, and what so I'm
So,
unable to think.
hmm. Yeah, so one thing is that if we, I mean, you are right that we can't really send the entire click to Bob because that will be a lot of communication. There are n vertices, and so let's size of v is n. Then in the worst case, Alice could have um, a click of size order n. In that case, she needs to send n log n bits. So this is something we don't want to do because we ideally we want quadratic in logarithm. So then the question is how do we send this information part by part, or can we do something like make the search space smaller and smaller every time. So the problem.
I have an idea at this point that can't Alice the local computation of Alice could be that she sort the elements and Bob also sorts the element of his set, and now the comparison will take place in between the first element and the first element. So there would be a matching only if there is no matching with the first element. So because both the lists are being sorted here. If both the lists are sorted, then the first element will get mapped to the first element. And then, how to compare, say, two strings and to compare two strings and the two sorted strings. So if A appears here, and then quite possible that this is B A kind of a thing. No, no, that idea won't work. I'm sorry, please continue. Yeah.
Yeah, but actually you are not very far from the there are two key ideas here. One key idea is that um, let's say I look at the click, so I'll not write the protocol, but I'll just convey one idea. So the first one is that um, if I have a click here, Alice gets some click. Okay, then notice that she doesn't really need to send. Let's say this was the largest click, and there's no extension. This is maximal in that sense. May not be maximum, but it's a maximal click. So you can't increase its size by adding more vertices into the set. Okay, so now Alice doesn't really need to send all the vertices. If she just um, if she just sends one vertex, okay, then Bob would have a lot of information about the entire click because let's say this vertex, I'll call this u. If she sends u, then Bob Bob does have access to the entire graph, so he can look at what are the neighbors of u, and let's say he finds this ABC, and then he can see that AB form an edge, CBC form an edge, and AC forms an edge, and so on. So he does know what the click is. The only problem is that there could be these extra edges that do not take part in the click, which is because this click is not maximum and so on. So there could be extra edges that U has, which are not a part of the click.
Uh, yes, but then it's true. It's true that a common instance of the graph is shared in between the Alice and the Bob. Uh, but the but the thing is that since this click need not to be it could be a small click also. But then if it is a small click, then just by sending one information of one vertex, so Bob will never come to know.
What the
Bob will
click
only
is.
come to know that it is a part of a click, and I mean these are the potential vertices which could be involved in the click, but will never come to know that which all vertices are actually included in
Exactly,
it.
exactly. So what Bob knows is something extra. So if C is the click, Bob definitely knows that C is contained in the neighborhood of U.
Yes.
Okay, so we don't really know which of these are useful for us, which are actually part of click and which are actually not part of click. So for that we need to do something extra. But one way to save the amount of communication is that one vertex carries a lot of information about the click. Okay,
Yes.
yeah.
Yes.
And
Uh,
the other idea that
but then I have a point here
hmm,
that if even if Alice sends a vertex to the Bob, then to represent that vertex, how many bits are required?
hmm,
So number of bits required won't be log square of n.
it
It
will be
would be
just
log of n.
exactly, it will be just log of n.
But
So
then in the question they have asked to get the solution in log square of.
hmm, because this log n is not sufficient to solve the question. Like you said that we don't really know which of these vertices are in the click and which are not. So we'll have to do some kind of divide and conquer, which you said earlier, that sort of communicate log n amount of information over and over again, do some kind of a binary search for log n number of rounds,
Yes, yes.
so that altogether log n amount of communication for log n rounds. So this will finally give us an order log square n protocol. Okay, and Okay, I'm not sure, just to mention, I'm not sure if this is the best upper bound that is known. Um, but I think, yeah, there's quite a lot of papers on this problem which try to prove some lower bounds and so on. Um, yeah, I'm not sure what the results are, but if you just Google search it, you'll find a lot of papers in case you are interested. But we'll see one simpler algorithm which gives an order log square in bound. Okay, so hmm, yeah. Hmm. So the idea too is that similar to what you said, okay, I don't, yeah, I didn't come up with this algorithm when I tried. So I don't know how one would have arrived at it, but the idea is similar to what you said. Okay, so you're going to sort the just locally sort the vertices. Okay, and um, so let's say one, then she has, let's say, 4 and 100 and so on, whatever. And um, Bob is also, so this is at Alice's end, and this is at Bob's end. Bob is also going to sort the um, vertices. Okay, so okay. Okay, let me just think of the correct case. Mm. Hmm. And let's say Bob has 101, 110, 142, and let's say 150. Um, okay, and let's say size of V is 150 for us, just for now, for this example. Okay, now one thing is that if the largest vertex that Alice has is smaller than, so the last element, the highest or largest element, if largest element of S is smaller than the smallest element of B, then what does this say?
So if the largest element of S is smaller than the smallest element of B, if largest element of, so that would mean that nothing is common, and then C intersection I is equal to Fi.
Exactly, then A intersection B or C intersection I in our case. Yeah, I should call this C and I actually. Uh, hmm. Then that would mean that C intersection I is equal to phi. So this is some kind of trick that we are going to play, but instead of communicating it this way, what works for us is that we'll do some kind of a binary search sort of a thing. So first you communicate. So let's say that currently the graph has um, the number of vertices in the graph is n. Okay, then Alice checks if she has um, an element, if there is an element of degree greater than n by 2 in S. sorry, in C. And if yes, then she will send a 1. If no, then she will send a 0. So the advantage of doing it this way is that she doesn't need to communicate the largest element that she has, which in this case it could take log n bits.
Yes,
Hmm.
yes.
So if we do it this way with a half-half sort of thing, then the queries are already fixed and they're just going to answer in yes and no type of answers. So if yes, then she sends a 1, and otherwise 0. Okay. And now Bob, what does Bob do? Bob checks if. So there are two different conditions that we are checking. Here we are looking for the largest element, and here we are looking for the smallest element. So the opposite question would be whether Bob has of degree um, at most n by 2 in I. And if the answer to 1 and 2 is no, I'll write it somewhere else. So um, if the answer to 1 and 2 is no, that means Alice, yeah, that means all the vertices in Alice's set C have degree at most n by 2, and all the vertices in Bob's set I have a degree greater than n by 2, right?
Well, this point is actually not clear. When you said that if the answer to 1 and 2 is no, but then the
Hmm.
second condition is altogether different. Second condition says that, oh, it is for the Bob.
Hmm.
Right. I thought that this is for the Alice only.
Okay.
So Alice checks if there is an element of the degree greater than n by 2, and Bob will check that if there is an element of the degree less than or equals to n by 2 in 1. And if the answer of both is no, so degree is less than n by 2 or equal to in C, and Bob will also say, but then what's the guarantee that both the elements are same?
Both the elements are 0, as in
Both the elements are same. It's true that I mean if the answer of both is no, so if the answer is no, then what does it mean? That there is an element of the there is no element of the degree greater than n by 2 in C.
Hmm.
And
That means all vertices in C have at most n by 2 degree,
yes,
and if
and
they hmm,
what's the meaning of no for the second case?
that Bob doesn't have a vertex with degree at most n by 2. So that means all the vertices that Bob has have a degree more than n by 2.
Right, yes.
So that means we are in this case, right? Here, let's say n by 2 was 100. All the vertices of Alice have degree less than at most 100. All the vertices of Bob have a degree. I mean, we're not really talking about degrees here, but I mean, just look at those as values. All the values are greater than n by 2. So as we said that they can't have any intersection.
Uh, But even if we have an intersection, so what's the guarantee that both the elements are going to be same? So like in this case, what is happening that like say the I mean we have transformed the clique of the Alice into another vector, and wherein the elements of the clique have been represented by their degrees in the vector. And same thing is happening with the Bob also. Say the independent set of the Bob now has been represented by a vector of or by a set of. So every element has been
No,
replaced by
no,
its
no.
degree.
No, no, no. So we are not sort of representing them by degrees we're just looking whether there's a vertex of degree greater than n by 2,
Yes.
and we're just
Yes.
answering whether doing that local computation and conveying it to Bob.
Yes. Yes.
So
Yes.
yeah, and that's why I guess like I shouldn't have yeah pointed here, because yeah, those are different things.
Yes. Yes.
Okay, so all we know is that if both the answers are no, then we know for sure that there is no intersection. Then, therefore, if yeah, therefore, we can conclude that C intersection I is equal to V.
Right. Right. I understood now. Yeah.
But the other case that we need to handle is if the answer to either one or two is a yes.
Yeah.
So let's look at that case. So then what we need to do is if the answer to, so this is the case 1, this is the case 2. If the answer to 1 or 2 is yes, so without loss of generality, assume that Alice's answer is yes. Okay, the other case is also fine, but okay, let's go with this. Okay, then what does that mean? That means that there exists a vertex of degree at least, sorry, greater than n by 2 in C. Okay, and let's say let's say that U is such a vertex, one such vertex, there may be many. Okay, and now we'll use our first idea and communicate that to Bob. So at this point, the step 3 in the protocol, so I'll call this 1 2. Okay, then the step 3 of the protocol is that Alice sends U to Bob. Okay, so now we are going to use our idea 1, which is that, okay, sorry, um, just give me a second. Which way should the communication go? Actually, yeah. Um, so notice that in this case, at least one of these are going to be. I mean, either this is of degree greater than n by 2, or this is of degree greater than 1 by 2. So okay, I should have actually written, like, inverted the sign. So let me just do that. I'll make all the greater than as less than equal to, and all the less than equal to as greater than. It's symmetric, right? This, it won't
Yes.
affect. Yeah.
Yes. Yes.
So I'll just do that. Um, this was, yeah, less than, let's say, and I'll make this greater than equal to, and that will change the analysis here. So this becomes greater than equal to and less than. Okay.
Yes.
Okay, now this makes sense, because if okay, then we would have to assume Bob's communication. Anyway, let's go ahead with this. So if so that means there's a degree of vertex of degree less than n by 2 in C, and let's say Alice communicates that to Bob. So now, like we said earlier, what does Bob know? Now Bob knows that Alice's clique, the vertices in Alice's clique, are a subset of the neighbors, of U, including U itself.
But then, what was the answer of the first message in this protocol when the answer of both Alice and Bob is in no?
Hmm.
So if
Then our protocol
that
will terminate.
protocol will terminate.
Hmm.
And if the answer of anyone is yes,
Hmm.
and we assume that the answer of Alice is yes,
Hmm.
so there exists a vertex of the degree less than n by 2 in C.
Hmm.
And quite possible that the Bob's answer could be a no. And if the Bob's answer is a no, then that would mean what? That there exists a degree of the vertex less than n by 2 in the independent set as well. So if that is the case, then what's the guarantee that both the elements are going to be same?
Exactly. There's no guarantee. It may be that there's a common vertex, or maybe that there is no common vertex.
Yes.
So that's why we are continuing our exploration. Okay. So okay. So this is our log n bits of communication here, and here we used 1 bit. Okay. So yeah. So now Bob just knows that the click. I mean, all the vertices that are relevant for Bob, and Bob has a independent set of his own. Okay, now we just want to check whether these vertices have an intersection with these vertices. So we don't really need any information about the other graph. Like, the original graph is very large, it has n vertices, but we don't need any information about it, because all we care about is this information that Alice just sent, that the neighbors of u, that is the degree of u, is bounded by n by 2. So these are less than n by 2 many neighbors, and Bob just needs to check whether any of his vertices intersect with this set.
Yeah.
Right. So what really happened is that the search space for Bob and Alice has reduced to n by 2 from n. So think of it this way. Think of it as so if G is the original graph, then if so, this is what I'm drawing. Okay, this set n of u union u. This is the set that we got. Okay, then we are going to look at the graph G prime that is induced by this set. That means just look at those vertices and look at the edges that are there amongst them. Ignore all the edges that are going outside.
Yes. 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 Right.
So from yeah from a from an instance of size n, we have come to we have like shrunk our space to an instance of size n by 2, and now we repeat the same steps. Okay, again Alice is going to check um, whether for the new degree, and this is not going to be n by 2. Okay, because n is now n by 2. I mean, the number of vertices earlier were n, now the number of vertices is n by 2. That Does that make sense?
Yes. Yes. Makes
Huh.
sense. Makes
So
sense.
yeah, so now this is actually going to be n by 4, and yeah, she's going to check for this and send it to Bob, the new information. And also the degrees are changing because we might have deleted some vertices, so we're only looking for degree within G prime, and Bob does the same thing. With respect to the new n, Bob is going to check whether there's an element of degree at least n by 2. If at this point we get that both the answers are no, then we'll declare that um, the intersection is empty.
Yes. Yes.
Otherwise,
Case one. Yeah.
keep on
Case
going.
one. Yeah. Case one will act as a terminating condition here, right?
Yes. So this is a recursive algorithm. So
But then but then which values are sent by Alice to Bob? Initially, the if it is not a if it is not the terminating condition, then Alice would be sending which value? The information of U. And for the information of you, I mean, we would be requiring login number of the bits. And then the next time again, Alice would be sending some other vertex, isn't it?
Yes, yes. So we'll
So then,
analyze.
yes,
Yeah. So I'll just write two steps, then we will analyze this.
yes,
So,
yes, yes.
okay. So, anyway, I'll just copy some part of it. Just want to make sure that everything is on the same page. And then we say this part. Okay, this part I'll just write again. Third thing is that Alice sends a U with degree less than n by 2 to Bob, and now we have reduced the problem of size n to size n by 2, and we will repeat steps 1 to 4 again until it terminates. Okay, so that is our algorithm, and let's analyze the complexity. So like you said, in this case we ended up spending one bit, and here we spent log n bits. So in one round we are spending, sorry, just give me 1 second. Okay, yeah, so we were here. So in one round, yeah, you were saying that we are sending 1 plus log n amount of bits. Yeah.
Yes. And then in the next round, we would, we have reduced the problem of the size n to the size n by 2. It's okay. But then again, Alice would be sending one more vertex
Hmm.
in response. If it is not the terminating condition, then we would be requiring log n number of the bits again. But then the size is getting reduced. So n by 2, n by 4. So in fact, I mean, there would be log n number of the rounds. And then in every round, we require log n number of the bits. So then we could solve this in the of the order of log square number of log square n number of the bits. Yeah, right.
Yeah, got it. So in the second round also, in the worst case, we'll require this much, and we keep on dividing the size n to n by 2. So size here was n, then it became n by 2. Finally, it will become constant sized, and so the number of steps here is log n. So number of rounds is bounded by log n. Therefore, the total communication is at most order log square n.
Right, right. So from these two problems, the common recipe is that we need to identify that what are the local computations, number one, and which computation is the part of which computation needs to be communicated, and whichever computation needs to be communicated, what is the minimum number of the bits required to describe that communication? Yes, yes, I understood this thing. Yeah, thanks. Yeah.
Okay. Um, so
So in
just a
this.
second, okay? I'll just decide the order which is better. Um, Okay, let's do this. So yeah, I'll just recall some concepts, and then we'll go to the question. Okay, one second. Okay, so just to recall, we have this function f from, okay, and we want to compute. Alice has this part, Bob has this part, and we want to compute f of x comma y. Okay, and if you think of it this way, so every boolean, so this is nothing but a boolean function from 2n bits to 1 bit, right? So you can think of writing this as a truth table. So here you have values for x, values for y, and this is the value of the function. So this will be like from all zeros all the way up to all ones. These are how many entries? Um,
So there would be a 2 raised to the power 2n.
yeah, so these are 2 power 2n entries. Okay, so but it's more interesting if we visualize it as a matrix. So on this side, let's say you have all possible x's, which is all possible n bit strings, all zeros to all ones, and on this side you have all possible y's, x, and here you have all possible y's, so all 0 to all ones. So what are the dimensions of this matrix?
N cross n. So 2 raised to the power n into 2 raised to the power n.
2 power n to 2 power n. And what are the entries? So an entry here is going to be the value of f of x comma y. So instead of writing it linearly like this, we are just writing it as a table, as a matrix.
Yes. Yes.
So this is what we call the communication matrix. And these are essentially the same things, because here also we are here also the 0 1 values of the function, these are 2 power 2n, and here also the the 0 1 values is as a as size, this is 2 power 2n. Okay.
Yes. Yes.
So um, so the question is, can we use some information about this matrix to say something about the communication complexity? So can d of f, can there be some relation between the deterministic communication complexity of f and the matrix M? I'll just call it MF. Okay, so it turns out that if the rank of this matrix is very high, then the the deterministic communication complexity of f is also, is also bounded, lower bounded. So it is known that d of f is at least the log of rank of the matrix MF. So okay, and by rank we just mean that it's the number of the maximum number of linearly independent rows or columns. Okay, and the question is, can we also, is this, question is whether this is tight. Okay, so the answer is we don't know yet, but the popular conjecture called the log-rank conjecture is that there exists some constant c such that d of f is at most log of rank of mf um, I mean, to the power c. So it could be square, cube, or something, but some constant c. So this is the conjecture, and this is something we already know, log rank of mf. So it lies somewhere between the log of rank and some power of log rank, but this is something that we don't yet know how to prove. Okay, so what is the I'll just highlight this part. This is the conjecture. Okay, so question is, what is the best possible thing that we know here? Maybe we don't know how to prove this yet, but what is like the best thing we know? So um, okay, so I don't recall the year, but Lovett showed that the showed this upper bound of a quadratic okay, and then this was okay, actually he did something times log rank of mf, and later on this factor was also removed by um, and he basically improved this to order of square root of rank of mf. So we want to show something like log of rank of mf to the some to the power some c, but the best that we know is just rank to the 1 by 2. So there's some exponential gap here. We want something like polynomial in logarithmic, but we have, what we know so far is just, so like we are very far from the conjecture. Yeah, that's the story. That's all.
So, so what is the current situation? I mean, are we? I mean, so which is the I mean known upper bound, the
Yeah,
square root
this
of
is
the
the
rank of MF or this one?
hmm this is the best because this is worse, right? This is worse than this.
Yes, yes.
So this is what came earlier, and then Sudakov, yeah, they improved it to this.
Oh, I see. And what about this one? Is this a conjecture only? Say the
Yeah,
log of the rank of MF, and
this is
still we do
still,
not have any proof of it.
yeah, we want, ideally we want to show this, but yeah, we don't know. So there's a huge gap here.
So, but the rank will give the maximum number of the linearly independent things. So rank will give the concrete information available in the matrix, and which cannot be produced from the other vectors. I mean, so since the rank is the concrete information, and to convey that concrete information, we would be requiring log of that thing, log of the rank of this thing. Like say if the value of the rank came out to be say 100, then this would mean that there are maximum 100 number of the linearly independent columns. So if that is the case, then how to communicate this thing? So we would be requiring this log of this thing, that these many columns are maximally independent. Uh, yes, mix. I was just trying to justify the use of this log term here, log of the rank thing here, because rank gives the substance of the or the concreteness of the matrix. So, and to communicate this rank thing, we would be requiring the log of that rank. I mean, those many number of the bits are
Oh, okay,
required in
okay,
that
okay. No, no,
sense.
no. So, we're not really communicating the rank. It's just a bound that we have.
But since this belongs to the complexity class DF, and F is about the communication complexity,
Huh.
so it would mean that
So,
we need to communicate something, and to
huh.
probably rank is something which we want to communicate. or something related to the rank we want to communicate.
So all this says is that for any function f, the communication complexity of that function f to find out the value of f of xy for any xy, um, there's a protocol which uses these many number of communication bits and computes a value correctly, so that the amount of the communication that is happening may or may not even use the actual value of rank, but this just gives the bound on that.
Yes, it's okay. It's okay that that the calculation may not be using,
Hmm.
I mean, rank into the picture, but
Hmm.
whatever the calculation is using,
Hmm.
that somehow would be related to the rank, because rank would be the measure of the concreteness of the x and y. That how much of the x can be produced by seeing the y, how much of the y, I mean, that sort of a thing.
Hmm.
So clearly, rank is a measure of that. That's something which cannot be reproduced.
Hmm.
Cannot be produced, I mean, with the prior information.
Hmm.
We need to have, I mean, this much of the information. We need to have these many number of the maximum independent number of the rows or the independent number of the columns. So whatever way we calculate x and y maybe could be related to this solid thing, and which is rank. So that is how, I mean, that was my intuition just, and to communicate
Huh.
this rank thing, we would be requiring log of this stuff.
Yeah, but actually you need not communicate rank because both Alice and Bob know this function f of xy, right? They know the function, therefore they know the entire matrix, and therefore
Uh,
they can compute the rank locally. They don't need to share anything.
okay, okay, this is the situation I understood. Yeah, thanks, thanks. Yeah.
Okay. Hmm. Yeah. Okay. Good. So let's do the. Uh, mm, okay.
Okay, so in this case, the function is given P such that its communication matrix MF has the distinct rows. All the rows are distinct. And distinct would mean what? That all the rows are independent or something else?
They are not equal. So any two rows are not equal. So if this is 0 0 0 0, all zeros, let's say, then the second, I mean, all the rows have to have something other than this value. So they're at least one of the index should be different, so that they are not equal as strings.
Oh, if they are not equal as strings, then okay. Oh, all right, all right. So if they are not equal as strings, so in the case of the Boolean matrix, if two strings differ, would that I mean, so how to show that the rows are or the columns are independent in the case of the binary matrix?
So how do you show that rows and columns are independent?
Independent, I mean to say that one row or one column cannot be represented as a linear combination of the other rows or the columns, because then that will determine that whether I mean all the so what is the rank basically. To know the rank thing, we would be requiring the maximum number of the columns or the rows and which are independent of one another. And so the linear combination would mean what in this case? Because in the case of the normal values, we have some methods to show to determine the rank. But for the Boolean thing, but even if that is the case, then the say if because somehow because we need to show that this d of f is greater than the this thing n. So if I can show that this rank is somewhere around say, n square kind of a thing. No, no,
Uh,
rank is n. If rank is n, because this is the lower bound, I guess this is the lower bound that df is greater than or equals to n. So we just it is sufficient to show that the rank of the m of f is greater than or equals to n. Is
is
this
equal to 2 to the n, because we know
2 to
that, huh.
yes. But then this is just a conjecture, and this is not the proof. So
No,
can we
no,
use
no.
this?
This is what we already know. So the lower bound is something we know. Only this part is the conjecture. So this is something we know. This is something that is the conjecture. Whether we can upper bound it.
Oh, okay. Now I understood. Yeah.
Hmm.
If this is the case, then clearly in this matrix there would be 2 raised to the power n number of the rows, and then how many columns would be there? 2 raised to the power n number of the columns. So the rank, if all the rows are independent of one another in a case, so then the rank would definitely be less than or equals to the 2 raised to the power n,
Hmm.
not greater than or equals to.
Hmm.
So
So the um, like to get here, you need to use this information. This is the only critical information that you are missing right now. That all the rows are distinct.
yes, so if all the rows are distinct, that would mean that okay, so uh, if all the rows are distinct, then if you give me okay, so all the rows are distinct. So there would be, but how to use this distinctness? So at the most, how can I use distinctness is so there will be 2 raised to the power n number of the
Hmm.
distinct
Yes. Hmm.
rows, distinct rows.
Hmm.
Uh,
So,
yeah.
how many possible, um, how many possible values can there be? Like, what are all possible values the rows can take?
So rows can take values like say all the values are. I mean, possible values would be, but for every bit we have two possibilities, either
Hmm.
a zero or a one.
Hmm.
So therefore we have 2 raised to the power n number of the strings possible.
Is equal to 2 to the n. Okay. And you have to fill all of them. There are 2 to the n spaces that you have to fill. So each of them is going to take one value from this set that you have.
Now I have confusion about this y as well, because once I fix the value of x, yes, so there would be the values of y's as well. So what is the question? I could not understand question now.
Hmm. So you want to show this lower bound, and this lower bound, if we know this particular fact, the relation between the rank of the matrix and the communication complexity. So this does not use any. I mean, because we know the result, we don't need to do any kind of communication. All you need to show is that the rank of this matrix is this much, and the matrix is something that you already know because F is known to you.
So, but then how is that possible that the rank is greater than the number of the rows or the number of the columns? At the most, we can
It
have
can be 2 to the n. So actually it's 2 to it's exactly equal to 2 to the n. That is all you need to show.
yes. So, if I need to show that this equals to 2 raised to the power n, then I need to show that all the rows are distinct.
Hmm.
And since this is given in the question that all the rows are distinct, so therefore there would be 2 raised to the power n number of the distinct rows, and all the rows are distinct would mean that rank is 2 raised to the power n.
Hmm. Yeah. So yeah. So each of these rows take take values which can go from all zeros to all ones. This is the set that we have, and the size of this set is 2 to the n. So there are, for every row you have 2 to the n choices, but once a choice is made here you can't repeat it because the rows are distinct. So now you have to choose something from the remaining set. So basically you will end up using all the rows. So that means if I look at this matrix, it is going to be some permutation of all the way up to all ones. So it is going to be some so maybe this row appears somewhere else and so on, but need not be ordered, but it is going to contain all of this.
Yes, yes.
Okay, and now we need to prove that the rank of this is 2 to the n.
So that is 2 raised to the power n only?
Yeah, because they are all linearly independent.
Yes, yes, yes.
So therefore rank of mf is equal to 2 to the n, and that proves our question. Okay. um hmm?
So I have a query here that from where, I mean, what's the relation in between designing a matrix and then finding and then relating it to the communication complex. So
So
what is the relation?
um
I,
I
I mean to I mean to say that from the communication matrix is just a Boolean matrix only.
hmm.
But then why do we call this a communication matrix? Uh,
Because that information, because the matrix contains some information about how complex the function is.
uh, so how complex the function? But then I mean, where do we capture the complexity of a function in this matrix? What kind of
um,
the what kind of the complexity is being captured through this matrix, except enumerating the strings starting from somewhere to somewhere? That's it. So what kind of the complexity is being captured here, and which is useful from the communication viewpoint?
so so at the moment all we are doing is we are just finding the rank of the matrix, um, because we are assuming this result which relates the hardness, the communication complexity of the function with the rank of the matrix. When we
Oh,
didn't hide, I mean, we didn't prove this right now. So
yeah, I understood something from here. So if I have been given a matrix of the dimensions say 4 into 4, then what is the minimum minimum length of the description required to represent a matrix of the dimension say 4 cross 4? uh, I mean, so there is an idea like say minimum description length, MDL, minimum description length. So if I want to represent a matrix of the dimension say 4 into 4, then what would be the minimum length of the string and which describes this matrix? Because if we can find the minimum length of the string which can describe a matrix, so that would give us the communication complexity of this matrix, communication complexity kind of the thing, or the complexity of this matrix. Complexity in the sense that the minimum length of the string required to describe this matrix, and which has got 2 raised to the power n number of the rows and the 2 raised to the power n number of the columns. Probably that would be the representation of the complexity of this matrix.
okay, but what I'm saying is that this matrix is already known to both the parties, Alice and Bob, because they know the function f, therefore they know mf. So we don't need to communicate anything about the matrix.
Yes, but then this is, I mean, what's the meaning that this is known to the Alice and the Bob? Because this is a function and the Alice and the Bob. So Alice knows
Alice knows
her
f.
input X.
Alice knows x, but Alice also knows. So the function f is known to both of them. And Alice has some string x, n bit length string. Bob has some n bit length string y. But they can't compute it. um, I mean, it's not trivial to compute that, because although Alice has her part of input, that means her answer lies somewhere in this row. Okay, but she doesn't know the column. The column is what Bob is holding.
I could not understand this thing when you
Huh.
said that in this entire matrix, the, uh, there is one row and which is specific to the Alice.
So Alice gets this x,
Yes.
right, and Bob gets this y. Okay, and the answer lies somewhere here. We want to find out this x, f of x comma y. Okay, so Alice has this entire matrix, Bob also has this entire matrix because f is known to them. So if this is x, this is y, then they know what is the value. But why they can't compute? Because let's look at Alice. She knows this matrix. She knows the x. So she knows the answer should lie somewhere in this row.
Yes,
But she don't.
uh, but then the possibilities of the columns would be 2 raised to the
Would
power
be
n.
2 to the n, exactly, because she doesn't know what is Bob's column. Therefore she can't pinpoint which of this is the correct answer. Similarly for Bob, Bob knows y, therefore Bob knows the answer lies somewhere in this column, but he doesn't know the row of Alice.
Yes, true, I understood. Yeah, yeah, thanks.
Okay. Okay, and to see why exactly rank is capturing this, I think the answer would be in the proof of this, which is not fresh in my mind at the moment, but I think it's done in the lecture. So take a look at this, how the rank is connected to the communication complexity.
Yes, yes, I will see.
Okay. Um, yeah. Okay, so I just define this pooling set method, but notice that you want to show, we know the equality game, and let me just remove this plus one because we are not keeping this constraint that Alice and Bob should both know the answer. Let's say that only Bob needs to know the answer, then Alice sends her string, Bob checks whether they are equal, and Bob has the answer. So let's remove that plus one part, and notice that if I have to solve this using the previous argument, that d of f is at least log of rank of mf. So how do we do this?
So if we know that df is this thing, then we would be designing a matrix, and the matrix would be of 2 raised to the power n into 2 raised to the power n only. And then this log of the rank would came out to be 2 raised to the power n. So log of 2 raised to the power n came out to be what? N only. So therefore this is n.
But how do you show that the rank of the matrix is n? So what does mf look like?
So MF would be similar to the previous matrix, 2 raised to the power n number of the rows, 2 raised to the power n number of the columns. And but then there a distinct rows was given, and in this case that distinct is not given. However, we need to show that whether x is same as uh, but then in this case we need to show that this rank is equal to this. So but then how to show that I mean all the rows are independent of one another, and to show that the rank, that the rows
To
are independent of
to
one
see
another.
this, let's first write what does mf look like.
uh, I could not hear this thing.
Uh,
What?
to find this rank, let's first write down what mf looks like.
Okay, okay.
So let's say the first row is this, all zeros and then all the way up to 1 1 1 1. These two are equal, so answer should be 1. Everything else, all these are different from this string, so the answer should be 0 for all of them.
So probably I missed something here. So we are constructing this M of f, and so can you? So actually,
So
I
this is,
misunderstood this M of f. So M of f means what? This is
so
x. X
in the
towards the row
rows
side.
you have all the possible strings that Alice can have. In the columns you have all possible strings that Bob can have. So
Yes.
if Alice's string is all zeros, 0 to the n, and Bob's string is 0 to the n, then the two strings are equal, therefore we should output a 1. But everything else that Bob can have will be different from 0 to the n.
So like in this matrix, exactly one value in a row, exactly one value would be a one, and all other values would be equals to a zero. So in that case, clearly all the 2 raised to the power n number of the rows would be distinct in this sense. And since they would be distinct, so therefore rank of m of f would be equals to 2 raised to the power n, and therefore this d of eq would be equals to n.
So actually this is an identity matrix.
Yes,
Only
yes,
the
yes.
diagonals are 1, and we know that these are linearly independent. Therefore the rank is
Right, right, yes.
so this is something that just follows from the fact that we know the matrix. But let's say we don't want to use this result, and you want to design. We want there's this second method. I think you done some 2 3 methods uh, to find the um communication complexity. One is the fooling set method, um, and the other is the rank argument. Um, yeah, third would be, I guess, more, I mean, more specific to the problems, but maybe looking at the protocol tree. I don't know what, but yeah, there are several, yeah, bound the number of leaves or something. Yeah, so there may be more methods, but at this is something we already know that you just look at the matrix, find the rank, and you get a low bound. But let's say we want to use the fooling set method. Okay, which is okay. Okay, so recall that we have this communication matrix MF, and you have all possible strings x here, all possible strings y here. Okay, and this matrix is going to have some 0 1 values. Mm, okay, there are some values. Okay, now there is this notion of rectangle or a combinatorial rectangle. Okay, so what does this mean? Okay, so think of x as having all possible. It is the set of all possible strings that can be here in the rows, and think of y as all possible y's that you can have. And let's say that R is a subset of x cross y. That means out of all possible x cross y combinations, we are choosing some value. So let's say I'm choosing this value, this value. Hmm. Okay, let's say I just chose these. Okay.
But then these are the values of columns only. And in the case of the Cartesian product, we need to select something from the row. I mean the entire row. Take the Cartesian product of the one specific row, and then one specific column. Complete row and complete column, isn't it?
No. So one element of x cross y would be something like this. So this is basically set of all possible x comma y, x in x, y in y.
Oh, oh, okay, okay, all right, fine.
Okay. And so when do we say that it is a rectangle? It is a rectangle if and only if, in fact, x1 y1 is in R and x2 y2 is in R, then x1 y2 should also be in R and x2 y1 should also be in R. That means if I say that if I say that this is my, let me use some other color, I say that this is my combinatorial rectangle, then let's see whether this property holds. Okay, this 1 comma 1 is there and 1 comma 2 is there. Sorry, let me use, okay, some, so this is there, 1 comma 1 is in my rectangle and I'm indexing these by 1 2 3 4, let's say. Okay, and 2 comma 2 is in the rectangle, then by our definition 1 comma 2 should be in the rectangle and 2 comma 1 should be in the rectangle. That means this entry and this entry, they should both be in the rectangle. Okay, and this holds for all pairs. So if you look at any two elements, if this is there and this is there, then 1 comma 3, that is, this should be there, and this will be 3 so this will be 1 comma 2, that should also be there.
Yes, yes.
Okay, so you can't have something like this.
Right, yes.
And it's not necessary that they are contiguous. For example, for example, if you just look at this blue, just these blue squares that I've drawn, they form one rectangle, because I could just permute this. Okay, I'll just do a row operation and take this row all the way down there, then this four people will become contiguous. One they'll form one rectangle.
Yes.
Okay, and it's not necessary that, as you can see in the red rectangle, it's not necessary that they should all have the same value. It could be some of them are zeros, some of them are ones. We are not saying anything about the values. Okay, so in a combinatorial rectangle, there may be 0 1 values, but if R is a rectangle and for all x comma y in R, if the value of x comma y is equal to some b, always b in 0 1, that is, all of them are zeros or all of them are ones, then we say that R is a monochromatic rectangle. So for example, this blue squares that we drew, they form a monochromatic rectangle, whereas the red one is not a monochromatic.
Yes.
Okay, and okay, what we know is that okay, so this is the theorem that we did in the class, that if any partition of x cross y into f monochromatic rectangles requires at least t many rectangles, then d of f is at least log t. So what does this mean? So you are given this matrix and we are going to cover this using monochromatic rectangles only. So for example, I could choose this to be one rectangle, this is my second rectangle, this is my third rectangle, fourth and fifth, assuming that this is the matrix. So I can cover this with five rectangles, or I can even do better. Maybe if I permute this thing all the way down there, then this whole thing can be covered with one rectangle. The blue ones can be covered with another rectangle, and the remaining two zeros can be covered with one rectangle. So the question is, what is the minimum number of monochromatic rectangles that you need to cover the entire matrix MF? If that is always guaranteed to is at least T, then that gives us a lower bound on the communication complexity of F.
Okay. Okay.
Okay, and what is the fooling set argument? The fooling set, let's define the fooling set first. So fooling set is something that is almost a monochromatic rectangle, but just not a monochromatic rectangle. What does it mean? So S is a subset of x cross y, like earlier R was a subset of x cross y. So we say that S is a fooling set if the first condition is um, hmm, is that for all x comma y in S, um, mf of x comma y is same value. So all of them are zeros or all of them are ones. So this is similar to the monochromatic property. Okay, but the second property that was there, so earlier we said that if x1 y1 is in the set and x2 y2 is in the set, then we insisted that x1 y1 x1 y2 and x2 y1, both of them should be in the set. This is how we define rectangle. But now what fooling set says is that if this happens, then this basically means for all, either um, f of this is equal to okay, so just by previous property we know that f of x1 y1 is equal to f of x2 y2. This is because all the elements in the set S have the same, compute the same value. Then either this should not be equal to set or this should not be equal to set.
I could not understand this thing that f of x1 y1 and would be same as f of x2 y2.
So what this property says, the first property says that if you look at all the elements in the set S, they all will evaluate to the same value.
Why? Why so?
That is how we define the set.
Oh, okay, okay. Now I understood. Yeah.
So it is almost same as rectangle. So how did the monochromatic rectangle? We said that all the elements of the monochromatic rectangle will evaluate to the same value. Either all are zeros or all are ones. And if x1 y1 and x2 y2 are in the rectangle, then x1 y2 and x2 y1 should be there. Now this property is similar to monochromatic rectangle because they all evaluate to the same value. Either all are zeros or all are ones, but it slightly differs from the monochromatic rectangle in the second property, where it says that either this or this should not be equal to the set. That means it's not in the set. That's what we are saying indirectly, right?
Yes, yes, yes.
So basically this is equivalent to saying that either x2 y1 or x1 y2 is not in the set.
Yes.
Okay, so why is this useful? So we have this theorem which says that there's a lower bound on the communication complexity of F. So if you could show that the number of monochromatic rectangles required to cover it is at least T, then you have this lower bound. So this fooling set directly gives us a lower bound for this. So this is a simple observation that if there is a fooling set of size t, then number of rectangles or monochromatic rectangles required to cover MF is at least t. So by that you directly get this bound.
I could not understand this when you wrote this last line of this observation that if there is a pooling set of the size T, then the number of monochromatic rectangles required to
Cover.
cover cover. But I mean, how is that possible that we cover the entire matrix through the monochromatic rectangles only? I mean, we would be having some zeros and then some ones. So on one side, I pick only zeros. The other side, I only picks ones in such a way so that I mean these properties are being followed. And moreover, they could be non-continuous as well. May not be contiguous in the sense that we can swap the rows kind of a thing. But is there any proof available that if we construct these rectangles in this way, then the whole matrix will get covered?
Uh, so actually the trivial way to cover the matrix would be that you just take every cell to be one rectangle, right? So the most trivial way would be whatever be the values, this is your one rectangle, this is your second. Every cell is one rectangle by itself. Every
Oh,
cell is a
yes.
monochromatic rectangle by itself.
Monochromatic, right, right. Yes, yes, yes. And then we are trying to reduce the number of the monochromatic matrices. And if we can come up with just two, if we can cover this entire stuff by just two monochromatic matrices, then the complexity of the matrix would be greater than or equals to one, only one. Okay,
That
okay.
means, that basically means that there's just one bit of communication that is happening, right? So um, so basically what happens is once Alice makes one communication, she is actually reducing, sorry, so let's say Alice does some communication. These are Alice's string and these are Bob's string. She this does one, um, okay, let's say some bits of communication. Now Bob knows something about X. May not be directly, but somehow Bob knows something about X. So it's going to reduce the space, the row space of Bob from here. So this is redundant for Bob. Now Bob knows that I'm going to search somewhere here. Then Bob will communicate something that will reduce the space for Alice, the column space for Alice. Now they know that they need to play the game in this submatrix. So on, like eventually the goal is to come back, boil down to this one particular cell that they are interested in.
Yes.
Okay, so okay, so the fooling set method is that if you could just show that there is a fooling set of size t, then you have a lower bound. Okay.
Yes. Yes.
So then if you want to show here, let's say we want to use our fooling set method to show that the equality protocol requires at least n bits of communication, then it suffices to show that there is a fooling set of size 2 to the n. Okay.
Yes.
Okay, so I'll just
No, it's okay. I was thinking that how to cover this entire matrix and which is an identity matrix by using the minimum number of the monochromatic matrices and that too. I mean, yeah, yeah, I was thinking on these lines.
but you want to come up with a fooling set to try to construct a a set S, so just to answer to your question, in terms of the monochromatic rectangles, these are all ones, right? So you're going to require all of them. Like, this has to be one monochromatic rectangle, and this has to be some other monochromatic rectangle, because there's no way that you can come up with a rectangle where the rest the remaining values are also one.
Yes, that would be the
And then
violation of that
hmm,
tuple property.
hmm,
However, the remaining stuff
hmm,
can this entire thing can be considered as a zero chromatic.
hmm,
Because then if 1 comma 2 is the element of this, then we would be having the upper half wherein 2 comma 1 is also the element of that thing. So in fact there would be two monochromatic matrices here, but not two, but then there would be some 2 raised to the power n number of these monochromatic matrices here towards the diagonal side, and the remaining stuff would be the two remaining stuff would can be contained in just one matrix. So
hmm,
then therefore there would be 2 raised to the power n. I think matrices required to cover this entire stuff.
hmm. Okay, I need to check this then. I guess I'm not sure if I'll just check this, if it is necessary that you cover the ones as well as zeros, or is it sufficient to cover one of them? Because once you cover one of them, like either all ones using rectangles and everything else is. I'll just check this.
Sure, sure,
Yeah.
yes, yes.
Okay, but for the sake of our argument, which is pooling set, you need to construct this set S which satisfies these two property, that all of them evaluate to the same value. So in this case, let's say I want all of them. Oh, okay, just the charging went out. So let's say I want uh, these okay okay, so let's say I want all the elements in the set S to evaluate to 1. So this set here is 1 for me. This set here is 1. So what is a natural candidate for S? Let's say all the x comma y pairs that evaluate to 1.
Yes, so evaluate to one. So what is the question, that what is there inside?
What are the elements of, so which of these um, elements evaluate to 1? Let's say I'll put all of them into my set S.
So towards the diagonal side only, those I mean those
Hmm.
values are one, and all other are zeros.
Exactly. So this is set of all x comma x. Let's say we are just trying out um, for all possible strings in hmm. Okay. So let's check. Okay, let's say we want to show that S is a Fooling set. Okay, so the size of S is already 2 to the n.
Yes, yes.
So if we could show that S is a Fooling set, then we are done, because then you have a Fooling set of size 2 to the n. That means the uh, the communication complexity of f is at least log of 2 to the n, which is n.
So then what would be the value of f of x comma x then?
F of x comma x,
Yeah, when both the
these are
values are
ones.
same,
1.
so these are ones. So since these are ones, so therefore first property is being followed here of the Fooling sets.
Exactly. Good. So the I'll just call it monochromatic property, I'll not write it. Property is holds. That is for all x comma x in S, f of x is equal to 1. So first thing is fine. Second thing you want to show is that if x1 y1 is in S and x2 y2 is in S, then either x1 y2 is not in S. Okay, I should not say really not in S, but f of x1 by 2 is equal to 0, or f of x2 by 1 is equal to 0. This is what we want to show.
Yes, and for this thing, say 1 comma 1 is an element of S, 2 comma 2 is also an element of S. So either we need to show that 1 comma 2, f of 1 comma 2 is a 0, or the f of
2
1
comma
comma
1
2
is a
again
0.
is a 0. So then what is this f of 1 comma 2? F
f
of
is
1 comma 2
nothing
is a 0.
f is nothing but our equality function.
Yes,
So
so that is
so
0, that is 0.
so in this case actually both will be 0.
Yes, yes, yes,
So
right.
this also holds. So I'll just wrap up for now. Okay. So try to do the disjointness. Sorry, this is the greater than. Uh, so greater than is the function that Alice has x, Bob has y. You want to say 1 if x is greater than y and 0 otherwise. And show a similar argument for, again, forget about this plus 1. Show that d of gt is n using Fooling set method. The rank argument is easy, so try to come up with the Fooling set method. And yeah, I'll stop with that. Okay.
Yes, yes. So next class would be on Wednesday.
Wednesday.
Yeah.
Yes.
Thank you so very much. Yeah.
Okay.
Thanks.
Thank
Bye.
you. Bye.